Three, two, one. All right. Oh god. Immediately starting off like coughing and sneezing. All right. Well, welcome to the pre-recorded lecture for February the 18th for Math 266. Yeah, as per the announcement, I'm under the weather, so could not come to campus and do an in-person lecture, so we're going to do a pre-recorded one. All right. Okay. So let's just get to it. All right. So let's pick up where we left off on Wednesday for the quiz. So the logistic model for population is the following: the rate of change of a population P. I think I always say population. It could be people, it could be animals, it could be cells, or it could be atoms. It doesn't really matter. Any amount of things that you can count, we call that a population. But anyway, its rate of change is equal to a positive constant k times p times n minus p, where m is also a positive constant. Okay. And now remember, the way we formulated this was by looking at our general population equation, which says that the rate of change of a population is the births minus the deaths. And under the assumption for the logistic is that the births are a decreasing linear function and that the deaths are constant. All right. So we noted that it takes a bit of work, but you can prove that the solution to this differential equation, note it is a separable DE, so it can be solved, but it is a particularly involved one. But the solution cleans up like this, where the P naught here is the initial amount of the population. And the other thing we noted, and this is the main feature of the logistic model for population, is that the limit of this, as we go off to infinity, is going to equal m. And thus, as we noted, we called m the carrying capacity. So as a model for population, the logistic model is one that is that has gone to for quite a few different situations, especially when you've got a population you know should be settling down to a specific value, and the specific value m here is a positive number. Right, so this does a really good job for modeling populations where you have an expectation in the long run of things behaving stably, like in the long run it levels out to some value. Right, the usual Malthusian model doesn't really do great in long term because it would blow off to infinity, which, right, short term maybe it describes this going on, but long term is going to falter horribly. All right, and I don't think I stressed it in class, but I will stress it again. This is only true when the population initially is positive. Now, obviously, we are usually under that assumption. If you have a population of something, you want the constant to be, the initial amount to be positive. But it is worth noting that if this is negative, this limit actually does not go to m. And the reason for it is super subtle. If this is negative, this denominator can become 0. So when this is negative, you have access to the log of the negative of it, and then you can kind of sneak it in here for a time and get the denominator equal to 0, which of course is a problem. Your textbook goes for that computation if you're interested, but it is worth stressing this. And again, we only really care when a population is positive, but it is worth noting this is necessary, and in a little bit we're going to get some graphical justification for that. But anyway, so after doing all the hard work, you get that this limit is equal to m. So yeah, it's good stuff. So let's use a logistic model for population to do a little modeling of a disease. Right, so like I said, the logistic model is brought up when we want a long-term behavior of a population to settle to some amount. So disease is a good one to use for the logistic model, especially if you've got the following sort of setup. Let's say that we have a disease and we know that initially one person is infected and after a certain amount of time, another number of people are infected. So here I'm doing 1 day and 100, and that we are assuming that the disease will eventually infect everyone in our population, and the population is 1,000. So a disease that's particularly like horribly communicable, or in a closed environment where just everybody's going to get it. The logistic model does a great job here because the information I'm told is that the initial amount is 1, and that the carrying capacity. Ooh, that should be 1,000, not 100. Let me do it live. Ooh, there we go. Okay. And the carrying capacity is 1,000, because only 1,000 is the amount of people that can possibly get infected. And we are assuming that everyone, yeah, if you don't got it, you're going to get it, basically. All right. Yeah, and so that gives us this. And now, note there is still a parameter floating around, even though the initial population and the m have been replaced in our equation. And again, note I'm just plugging them into this right here. Okay, now how do we figure out what the k is, right? Because I want, to get a p of t that describes the number of people infected as a function of time. I need to know what k is, and I was told another piece of information, so this unknown parameter here can be solved for. Alright, and so what do? Well, right, replace t with 1, replace this with 100, and solve for k. And blip, there it is. So this is pretty typical stuff for population models that we've been seeing. Usual sort of work here. So note, first things first, I cancel out those zeros, then I cross multiply, subtract the 1, divide this over, take log of both sides, and something that I always do, and something you should maybe get in the habit of, is if you're doing log of 1 over something, just always turn that into negative log of the denominator, right? That's a log rule. And a lot of times in these population things we break the numbers, so this happens. And then we divide over by the negative 1,000 and get k is equal to this quantity right there. Beautiful. All right. So we now have our formula, and hey, it cleaned up real nicely, right? Because note, k is equal to log 11 over 1,000, so when I plug it back in, the negative 1,000 is going to just get knocked out. Also the negative log of that. All right, so there we go. This is a equation modeling our population as a function of t. All right, and now again, note, as we already established, if you let t go to infinity, this term down here is going to go to 0, and thus we'll get 1,000 over 1. So in the long term, everyone's going to be infected. Now, the thing about a population is that while we're using a differential equation to model it, a differential equation is a continuous piece of information. Right? Remember, if you're differentiable, you're continuous. So t, right, is a variable that exists in a domain that's not discrete. Meaning that, right, t can be any real number you want, which means that if I plug in a particularly goofy value for t, like pi, let's say, and do this computation, I'm going to get like a fraction. And since this is supposed to be a population, right, it doesn't make sense to talk about like a third of a person or something like that. So when we have this model, typically what we assume is that the output, even though it might be a decimal, you round up. Right, because if you have, let's say, the population, you plug in a time and it spits out, 20.7, then we take that to mean that, okay, you got the 20 So, in particular, if you wanted to figure out when virtually everyone is infected, so a time where you can basically guarantee everyone's got it, you just need to solve p of t for any value bigger than 999. It's over 900. Woo. And then solve for it. And this gives you an estimate of when virtually everybody will be infected. It's not equal to 1,000. And note, this never does equal 1,000. Its limit is 1,000, but it's never actually equal to it. So if you wanted to give a good guess as to when everybody gets it, you got to do something like this. And of course, these are gross decimals, so I would not expect you to be doing this on a quiz or an exam, maybe on a homework. But anyway, if you ask Wolfram Alpha to solve for this, it spits out that. So basically, in 3 days, you can guarantee everybody has got it. virtually, because again, this will give you a number, but it's not going to ever give us 1,000. So it's possible maybe that one person survives forever, never actually getting infected, but we can call it virtually everyone. Okay, cool. All right. Now, the main feature of the logistic equation is that when the time goes off to infinity, the long-term behavior, it settles out to the carrying capacity, the M. Now, in order to see that, you needed, of course, to solve the dE and then take the limit of the function, but as we noted, the computation of the function is particularly involved, so it would be great if we had a method of finding the limit of this function without actually computing it. And what if I told you you could actually do that? Ooh. So it turns out that for a very specific type of differential equation, we can figure out long-term behavior of our solutions without ever actually solving, which is amazing, especially because most dEs that come from reality are typically impossible to get solutions for. Yeah, kind of the joke is that in DiffyQ you learn how to solve dEs that nobody ever encounters, because these are just the dEs we know how to actually get answers to. In the wild, you get dEs that are just absolutely brutal and just don't have reasonable answers, and you have to do the following sort of analysis to them. So the dE that we're going to specifically talk about is what's referred to as an autonomous differential equation. So it's a differential equation that looks like the rate of change of an unknown function x with respect to t. So note, pay attention, the independent variable is t, the unknown function is x. So our unknown function's derivative is equal to some function depending only on our unknown function. So the right-hand side does not explicitly have the variable t. The variable t is buried inside of x. So a constant c is called a critical point if this function zeroes out, and note that those are precisely the constants, so that the constant function c is a solution to the differential equation, which we'll call an equilibrium solution because, well, it's constant. It's not changing. So autonomous dEs, we can always talk about their critical points. You just set the right hand equal to 0 and solve for it. And it turns out that these equilibrium solutions, these things that are guaranteed to be solutions of our dE, note they're very nice because they're just constant. It turns out that if you know where your critical points are and how your solutions are behaving nearby, you can figure out long-term behavior without ever actually solving. So let's see how you would actually do that with the logistic equation. Alright, the critical points, so you just replace the derivative with 0, must satisfy the following, and k is positive, so the only way this is true is if p was 0, or if this quantity was 0, which of course means that p was equal to m. So this reveals that our logistic equation has two solutions. This differential equation always has two solutions. If we were constantly equal to 0, or if we were constantly equal to m. And now note, our intuition already about the logistic equation, this makes quite a bit of sense. This is supposed to be a population. So if there is nothing, then yeah, the rate of change is equal to 0, and there you go. You don't have a population, nothing's changing. Yeah, this is a solution to the dE. Right. We'll place p with 0 in here, and you'll see that, yeah, you get 0 is equal to 0, dE is solved. And similarly, when p is equal to m, and you plug that in the dE, this satisfies it, because you'll have 0 is equal to 0 again. And that makes sense, too, because as we noted, the m is sort of like the maximum amount the population could have. So if you're already starting with the maximum amount you can have, you don't change. You just stay there. And let's make that a little bit more explicit now by looking at values of p near 0 and m. So we're going to look at values near the fixed points. If p is less than 0, okay, well, m is positive, so that would mean that p is less than it, so m minus p is positive. So k is always positive, so the p here is negative, and this is positive, so overall it's negative. Meaning that any solution whose outputs are less than 0 must be a decreasing function, right? The derivative is negative. So if we had a solution, and I know that the solution's outputs are less than 0, then it's got to be decreasing. And now note that I know that if my solution is less than 0 anywhere, it's less than 0 everywhere, because it's decreasing. So it never gets above 0, it always stays below. Similarly, we can continue this analysis by looking at a p that lives between 0 and m. Here p is positive, and this means that m minus p is positive. So we got positive, 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 all things positive. So any solution whose outputs landed between no population and the carrying capacity must be an increasing function. So if our p naught was positive, then our solution lives here, and it's increasing, meaning that my function must be headed towards m. Alright, and now the last case is what happens if we've got a p above the carrying capacity. Alright, well then this is positive and that's negative, so the product ends up being negative, so any solution above the carrying capacity must be decreasing. So, if our p is positive, it doesn't matter which case we're in, if the p did not exceed m or if the p does exceed m, our function is decreasing there. So here we see that if you're a little bit below 0 or a little bit above 0, you're going to get blown away from it because you're below 0, so you'll decrease away. And if you're above 0, you increase away. And likewise, if you're above m, then you'll decrease down to m. So the last 2 points here specifically reveal to us that as long as our initial population is positive, then in the long run, my solution must be headed towards the carrying capacity m. Right, if it's below it, it's increasing, strictly so. So it's got to head up towards it because it can't not. And if it's above it, it's got to crush down to it. And a piece of terminology we use here is that p equals 0 is unstable, right? And I can't already let that slip because if p is less than 0, it decreases away from it. And if p is bigger than 0, well, it increases away from it. So if you're nearby 0, you'll get pushed away. And p equals m, the carrying capacity, is a stable fixed point. Because if you're right below it, you'll get pushed up to it, and if you're right above it, you'll get pushed down. And I already let it slip, but this analysis reveals that the limit has to be m, right? Just by the nature of things. If our initial population is positive, then we're only in one of these two cases, and if you're below m, you have to be increasing up towards it, and if you are above it, you must be decreasing down towards it. So the limit has to be m. It can't go anywhere else. So note, I got this information by just setting my equation equal to 0, figuring out the fixed points, and then checking where it's positive and where it's negative. Right, because it's a derivative, so it gives me rate of change information, so it can tell me where the function's increasing and decreasing, and thus we see that, well, the function only has one place to go. It has to go to m. If it's below m, it increases up. If it's above m, it decreases down. It's gotta go to m. Beautiful. So that's information that I can get about my solution without ever actually computing it. That's very powerful. And what's even more powerful is this idea of a slope field. So as I already let slip, this is a derivative. Knowing when it's positive and negative tells me when my function is increasing or decreasing. So given an autonomous DE, so again a DE where the right-hand side only depends on the unknown function x, it does not explicitly depend on the independent variable t. So for each x, we can compute f of x, and that tells us what the slope of the tangle line, the tangent line. Oh man, what do you call a British person on the beach? A tangent. Alright. Anyway, so yeah, this will tell us the slope of the tangent line needs to be. So if we were to pick a bunch of values of x and plot them out, that'll give us a picture of what the solutions are going to be doing. So if we look at dp dt of m1 minus m, here this is a logistic model where k is 1 and m, this is supposed to be p's, oh my god. Ugh. This is what happens when you make slides hopped up on cold medicine. Ugh, math, not even once. Alright. But yeah, so here's the slope field for this. Here k is 1 and m is 1. And ooh, look at this beautiful picture. That's gorgeous. Right, so note, at 1, which we know is the carrying capacity, our lines are nice and flat, because our solutions, if we started at 1, are going to stay at 1. Right, it's an equilibrium solution. And if our solution starts at 0, it'll stay at 0, because it's an equilibrium solution. Okay, but note, if the initial value starts somewhere in here, well, it's increasing. And if we follow the lines, the slopes tell me, hey, I'm headed up towards there. Likewise, if I'm up here, the lines decrease down. So in the long run, any solution that starts above 0 is going to be attracted to 1. So the equilibrium solution of 1 is a stable fixed point. And here we see that for 0, if you're above it, you blow away, and if you're below it, you blow away as well, you go down. Alright, so again, this is graphed by, just, and this is t versus x, just picking an x value and plotting the graph. Now note, of course, we're autonomous, so we don't depend on time, so note, if you were to slash vertically down, you'll see that the slopes are all the same there. That's because there's no time dependence. If there was time dependence, then, right, yeah, this would be a much more interesting looking picture. But yeah, there we go. It's beautiful. Alright. So let's do this analysis again on another DE. One that we don't know what the answer is to immediately. And let's use the knowledge we just gained to tell you long-term what this solution, what a solution to this is going to do. Okay, so first of all, we'll get the fixed points. Alright, well, obviously, x squared minus 16 factors out nicely, so plus 4 and minus 4 are the equilibrium solutions. And we, again, will check the values of x near these points. So, right, hopefully this is very reminiscent of something we did in calculus. This is finding the intervals where a function is increasing and decreasing. Alright, so for x less than minus 4, the derivative is positive. For x between negative 4 and 4, the derivative goes negative. And for x bigger than 4, the derivative goes positive. So our function is increasing if our outputs are less than 4, decreasing if they're between minus 4 and 4, and increasing if they are bigger than 4. So in light of this, we have that x equaling negative 4 is a stable fixed point, because if we are below it, we increase up to it, and if we're above it, we decrease down towards it. And x equals 4 is unstable, because if we are below it, we decrease away from it, and if we are above it, we increase. And note that now I can tell you something. And I gotta fix it. Hold on, give me a second. So note now, I can tell you some long-term behavior. So note, if our initial value is anything less than 4, the 4 is the unstable point. Oop. Fixing it. Give me a second. Alright. Okay, got it fixed. There it is. Okay. Alright, so in light of this, we have that x equals minus 4 is stable and x equals 4 is unstable. And so note that if our initial value is anything less than 4, right, if we are below 4, so we're in either one of these cases, well, if we are above minus 4, we'll decrease down towards it. If we are at minus 4, nothing's going to happen because it's an equilibrium solution. And if we are below minus 4, then we'll increase up towards it. So I don't know what the solution to this DE is. And again, it's separable. You could solve this if you wanted to. Now, whatever you get, as long as the initial value is less than 4, the long-term behavior of it has to be 4. That's the stable equilibrium point. So that's one we have to head to, unless we are too far away from it, right? If we're above this, then the instability of it will blow us away. But if we're below it, then the limit will go to minus 4. Beautiful. So this sort of analysis is something you'll do if you ever, depending on what you're going to do in your math life. I have no idea what you're going to do. But if you're ever in the situation where you have differential equations modeling something, this sort of analysis is something you'll do first. You won't try to solve it, because most DEs in the real world are incredibly difficult to solve with a closed form answer. So this sort of analysis is something you usually do first, where you're like, okay, well, all right, is it autonomous? All right, it is. What are the equilibrium solutions? And then see how the derivative is behaving. Right, and that'll give us some stability information that lets us make these sorts of really nice predictions. Getting answers without actually computing the answer. The best kind of mathematics. Beautiful. All right, nice. Okay, so something that we've seen here are equilibrium solutions that are stable and unstable. Now, it's worth noting that it's possible that you get equilibrium solutions that are neither. And it's really easy to cheese this because you just take something where the sign, SIGN, is not going to change on the right-hand side. So this DE, which note is super easy to solve for, it's separable, there's no partial fraction, so easy to do. The only fixed point for this is 0, and note that the derivative is always positive whenever we're not there. So if we are below it, we'll increase up towards it, but if we're above it, we'll increase away from it. So we call such a critical point semi-stable, and if we look at the slope field for it, we see that behavior. Right, if we're at 0, there's no rate of change, so we're at the equilibrium. But if we're below it, we'll increase up towards it. But if we're above it, we'll increase away from it. So you're not stable, you're not unstable, you're semi-stable. Right, if you're below, you'll come up to it and settle down, be nice and happy. So note that any solution whose initial value is below 0 will have a limit of 0 as t goes to infinity, but anything above it, the limit blows off to infinity. Cool. Cool. Alright. So, one last thing to discuss with all of this stuff is the following. So, when DEs are being used to model phenomena, there's usually parameters showing up in your equations. Right, we saw that with the logistic, there is a K and an M that are these fixed constants, and depending on the values of those things, your solution may exhibit different behaviors. So here's a very famous example. Let's look at the rate of change of a unknown function x being r times x minus x squared. All right, so note there is a parameter r here, and note that the fixed points, set this equal to 0 and solve. Note that there are two fixed points, potentially two. 0 is always a fixed point, and r is always a fixed point. Now, the stability of the fixed point 0 in particular is going to change as r changes. So note, this fixed point always exists, but its stability is dependent upon r. So if r is negative, then the rate of change is going to be positive when x is between r and 0. Right, so x is less than 0, so that is 0, but x is less than this, so it's r minus x, so that is also negative, so you get negative times negative, meaning this is positive. And likewise for x being bigger than 0, the rate of change will be negative. So this is stable. If we are below the fixed point is 0, then the derivative is positive, so you increase towards it. And if we're above it, the derivative is negative, so we decrease down towards it. And this sort of analysis is a lot trickier to handle because there are two things running around you need to keep track of. You need to keep track of where x is, and you also need to keep track of where x is in relation to r. So in terms of like inequalities, this ends up being like really tricky to work with, right? Because up at this point in your math career, inequalities sort of exist, but you don't really work with them that much. So doing this sort of analysis initially is a little tricky to get used to. But it's not too bad, especially if you kind of break it down like, okay, where's r? Think about where r is. All right, when r is 0, our DE is this, which is the same thing as the DE we just looked at, only it's negative, so it's always decreasing. And so it's semi-stable. And then likewise, if r is positive, then, right, we look at x values near 0, so that's not right there. That should be x is less than 0. Let me fix that. Very professional, I know. All right. Yeah, but so when x is bigger than 0 and less than r, so when it's near 0, then the derivative is negative. But if it's below 0, the derivative is positive. So above it, no. Hold on. Wait, what? What? What's going on? That'll be positive, but you're less positive. That's positive. Oh my god, I'm smoking. I'm on that back, yo. Those inequalities are backwards. Oh, yeah, I know it needed to be unstable, just by the nature of how this stuff works. It's like it's got to be stable, and semi-stable, then unstable, because it's continuously moving. I was like, wait, those aren't right. Yeah, no, those weren't right. But anyway, fix it. That's good. But anyway, yeah, right. So when x is bigger than 0, then the derivative is positive. But if it's a little bit less than it, the derivative is negative. So, right, if you're above it, you blow away from it, and if you're below it, you blow away from it. So it's unstable. And this sort of phenomena where altering a parameter in your autonomous DE changes the stability of your solutions. Right, so your differential equation exhibits, our solutions to our differential equation exhibit qualitatively different behavior. These are called bifurcation points, right? Because right at r equals 0, we bifurcate. Some massive change happens to our system. When r equals 0, right, we're semi-stable, but below it we're stable, and above it we're unstable. Cool stuff. And this stuff right here, studying things called bifurcation points, big stuff in in a branch of math called dynamical systems and chaos theory, where you study this sort of stuff all the time. And note here, this is kind of the logistic equation with k equals 1 and r here acting as a carrying capacity. Obviously, in practice, like negative carrying capacity doesn't mean anything, but we see the behavior of x, though, changing as you change the parameter. That's what matters. Cool stuff. All right, neat. All right, so with that said, that covers everything that we need to cover for our exciting exam next week. So we've got all the material covered. On Monday, we will do a review. So we'll also do a little bit of review on Wednesday. Then we'll take our fifth quiz. Can you even imagine? Let's see, our fifth quiz. And on the Friday, we'll take our exam. Cool. All right. All right, so that's it for today. Thanks for joining me today, and I'll see you. I should see you in person on Monday. I tested negative, so I don't have the Rona, but I definitely wasn't feeling too hot the past couple of days. I was sort of feeling a little sick on Wednesday. Like I got really sweaty towards the end of class. And then I have another class following ours, and when I went there, I was just like a train wreck. It was like, I gave like an absolutely terrible lecture in that class. Yeah, anyway. Alright, that's it for today. I'll see you next time.